Hi everyone. Okay, let's start. Welcome back to our last class of CPE 460, Introduction to Edge AI Technique 1 Machine Learning. But first of all, let's have a brief review of the principal component analysis, which we introduced in the last lecture. So first of all, we mentioned that the PCA principal component analysis is a technique of data dimension reduction, and the data dimension reduction is used to transform a data set from a high dimensional feature space to a low dimensional feature space. And while we need to preserve the most significant info of the original data set. And we have some examples here. Let's just skip those examples. So here, by mentioning the most important info, what does that really mean? Most important info. So here we mean that it needs to, the data set along a direction that it differ the most, or let me see, differ the most. And what does differ the most mean? So the difference here can be quantified by the variance of the data projected onto that direction. So here, directly we have three questions. First of all, what is the mathematical expression for the variance of the original data set? In the original feature basis. Second is since we set the variance of the data projected onto that direction, we to compute how to compute the variance, not only in the original feature basis, but also project onto the direction that we're looking for. Third is when to determine the expression of the most significant, the second most significant, blah, 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 till the p most significant directions, where p is the number of dimensions in the original feature space. So these are the things. First of all, we found the mathematical expression of variance in the original feature space, which is where this, I will skip the mathematical, derivations here, which is right here. So the y is, any annotation for any variable generated from this data set distribution. So we can get this one, where the z is the mean centered version of the data set, which is nothing but, just each row vector of the data minus its bar. Bar means the summation of everything divided by n, the total number of data. That's it. And then the second thing is we to project the data onto the new basis, which is the PC basis. Suppose we've already solved the problem number C, that we know what is PC basis. Okay, so first of all, we should have a look at the projection. So suppose I have an X in the original feature base. The coordinates are X1 and X2. In other words, I have X equal to X1 I1 vector plus XI2 I2 vector. Again, I1, I2 are unit vectors, of this, meaning these unit directions. And then I want to project X onto V1, V2, a new coordinate space, or a new basis. What shall I do? Actually, the new coordinate is super simple. It's nothing but the inner product of X and V, the corresponding vector. A super easy understanding, as you can just consider like the physics, which is, for example, you can consider like the physics effort. Suppose you have a distance, you have distance vector, you have a force on it, but there's an angle, let's say theta. So how would you compute, right, the force along that direction? Isn't it the inner product of your force and your direction? So here's exactly the same. So by the inner product, we can easily and directly get the corresponding coordinates onto the new onto the new feature basis first. The second thing is, well, you've already known this, then how can you compute the variance? Very simple. Again, by this formula, which is, I believe, here. Yeah, because now, remember our Z matrix, which is the data's mean-centered, version of the data set. So what you have is, for each data, you have what, a V, you just project onto V1, project on V2, V3, right? what you're gonna have is, so since remember variance, the notations here, then what you're gonna have is you're gonna multiply a left v vector and the right multiply the same v. So what you're gonna have is here. That's what I'm saying here. So you just plug in the thing and then you directly can get this one. In other words, we've solved the problem number B, which is, project onto the new basis and derive the expression for the new variance on this new base feature basis. Okay, problem number 3 is, well, in the second problem, we assume we know a PC, but which one should I be the PC, right? So here I introduce, first of all, wait, sorry. Here's an example to verify that this formula is correct. So first of all, here I use the very traditional definition of variance to brutally compute the variance of of these 2 points. Where here v is the vector. I mean, I honestly just randomly choose a vector. It doesn't matter what is v. I just randomly chose the vector here v, and then I project original data x1 onto v and then x2 onto v as well. And then here first I brutally compute the variance, which equal to 0.5. Then let's directly use this formula, and you can see the result is also 0.5. Time limit, I'm not gonna verify it step by step. You can simply verify it, after the class. So this shows, this formula is correct. After it, we mentioned how can we find the first PC, and after we determine, we define the second, third until the PC. But excuse me, by the definition, the first PC is the direction along which the data set varies the most. And we've already got, the derivation, the expression of, to any direction V, what is, the variance. So in other words, you want to, derive the most. In other words, the variance the most. And hence, you want to maximize this function, right? Since 1 over n is a constant, why? Because, I mean, n is simply the number of training data, so that once you get a group of training data, you immediately know how many data. So it's a constant. So we can just simply ignore it in this maximization function. In other words, you want to maximize this VTZTZV, where the decision variable, or should I say decision vector, is V, subject to the norm of V is 1, meaning that V is the unit vector. And then, we use the KKT conditions, and then we just, derive, and then finally we realize this is nothing. The V is nothing but the eigenvector of ZTZ corresponding to the largest eigenvalue. That's it. So this is the first PCV1. And then, by we just naturally pass it to be here because I didn't show any mathematical proof or something here. We just naturally pass it. So the second PC, for example, is the eigenvector of ZTC corresponding to the second largest eigenvalue. The jth is corresponding to the jth eigenvalue. And hence we defined accurate, mathematically strictly defined all those PCs. And then our job looks, is done here. So that is all the idea of the PCA. I can fully understand many of you may not be very familiar with those math notations, something. I know some people may ask, so what's the point? I mean, in this class, you introduce the mathematics. Well, here's the key. First of all, you don't have to, you don't have to memorize all these math formulas. Really, nowadays the world is pretty, it's very open, right? I mean, you don't have to memorize everything. If it's really something needed, you can always, just check the internet or just check, go back to the slides to check. However, you must know what? You must know the idea, the logic behind this very clearly. Why? Because simply, for example, in the homework something, you can just, I mean, I can show you, for example, use PCA, like the final exam, I'm going to say use PCA to do this like data reduction, use 10PC, for example, to reconstruct the image or something. Yes, it will be. But in the practical thing, let's say in your job, you have something you realize that, hey, I may be able to use machine learning to solve this problem. Nobody will tell you the method, saying that, oh, hey, you can use PCA, for example, to do the data, dimensional reduction. Nobody will tell you. You see what I mean? And hence, you need to know what PCA exactly, I cannot say exactly, I should say at least roughly is, so that you're gonna know, oh, it's actually nothing but just a rotation of the different, the coordinate system, the feature basis. and then reducing the number of features by what? By here, which is the explained variance threshold alpha. That's it. That's the basic idea. And hence, you know the background, you know the logic and idea of those models, then you can choose. Okay, I have this problem. Then which model should I choose to solve it? You know what I mean? So that is the thing. So true, a detailed math you don't have to know accurately, but the logic, step by step, we get A, then we get B, then we get C, and what's our purpose? This is the most important thing. You need to know how to handle this, because really, again, in a practical problem, nobody's gonna tell you what method should you use and step by step. No, it's not like a problem like a exam or something. You need to know which model to use and how to know which model to use. That is, you need to know the background of the model. So that's the thing. Okay, so here is a term as a term here, which is the ZV, which is a score. Actually, this is nothing, just the coordinates. The coordinates. In the new basis for each data point. That's it. Each data point. What I mean is that the mean shifted data point. Okay, it's mean shifted, not the original one. So that's the meaning of the score. Finally, how to determine that in detail about how many dimensions can be reduced. So here we have the total variance, which is nothing but the summation of the eigenvalues divided by n. Be careful, total variance, that means the summation of total variance, meaning that you need to compute all those p's, all the eigenvalues of the ZTZ matrix. And then we have the so-called explained variance, which is from J, the case experience, the explained variance, which is from the summation from J to K. The first K, summation of the first K lambda J, that's it. The first K lambdas, eigen values, that's it. And then we will first define, have a user-defined threshold alpha. Of course, it's between 0 and 100%. And then we're going to compute from k equal to 1 equals k equal to 1, 2, 3, 4, 5 until we find the smallest k that satisfies this RK, the explained variance ratio to total variance ratio is greater than or equal to alpha, the smallest one. Then we're done. So that we will reduce the original p dimensional feature to the new k dimensional feature, where k is less than or equal to p. In most cases, k is less than p, not a little less than p. I mean, I already finished the final exam. So in the final exam, you will see a huge reduction actually. So and then here we show the example. Basically, it's just a manual calculation of a super baby simple example of 5 points. So original space is 3D. You can see 1, 2, 3. I have 3 features. So here's the generate the center shifted Z, and then compute the eigenvalues and eigenvectors. I did it on MATLAB, so you can just do it, for free. You can use the Python, use NP dot linear algebra algorithm to compute it as well. It's just you can just search it, super simple. And then we get a first PC. Why this is the first PC? Because it's corresponding to the largest eigenvalue. You can see I have 3 eigenvalues, 4.1, 161, and 486. So 486 is the biggest. Its corresponding eigenvector is considered as the first PC. Similar things. This is the second biggest eigenvector, eigenvalue, and hence the corresponding. This is the eigenvector. It will be considered as the second PC, and this is the smallest PC, and the smallest eigenvalue, and the corresponding eigenvector will be recognized as the third PC. That's it. And then we show the example about if alpha is 90%, then how many PCs are needed? 2 PCs, because you can see the first R1, it's only 74% of the variance can be explained, while when I increase k equal to 2, then I can explain 99.36% of the variance, and it's already bigger than my alpha 90%, so it's enough. By comparison, if my alpha level threshold is only 70%, then indeed the first PC is enough to explain, the variance. So that's it. Okay, and then in the last lecture, I remember, yes, I remember I did it. Let me have a look at it just in case. Yes, I did this example. So this example basically is just I created 3 points as a make. Oh wait, actually, it's exactly this example actually. Yes, this is the same example, but this just show you how to use Python do it. First model PCA model fit, and then we have the model components. So model components gonna give you the PCs, and then we print the PCs, which is the PCs are here. And be careful if I don't put any components here. If I don't put anything here, let me run it again. Okay. Oh, sorry. And then here I want give me. Okay, here we go. So n components equal to none by default, meaning that if you don't write any components here, it will just give you a complete PCA principal component analysis. It will give you all the three PCs since it's a 3D, So these are the three PCs. You can definitely say n component equal to how many. Then it will, that is to make the dimensionality reduction. Okay, so here we have something called individual PC, individual explained variance. It's actually a super simple. The so-called individual, it is right here. That remember here we have this is explained and this is total right. Individual means for each day. That's the individual lambda. That's it. And you can see, for example, here I've already computed it's for 86, 161, 4.1 something. And then you can see here, it's, oh, wait. Individual explained where, where I meant one, but something's wrong here. Let me see here. Okay, I know why. This is somewhat, okay, so in Python, it automatically add a shrinkage, not in Python, in scikit-learn library, automatically add a shrinkage parameter there. And hence all the numbers are like a shrink. But if you compute the ratios, they should be the same. And here is the explained variance here. And then here is the so-called, this is actually the score. Remember what is the definition of score? Score is just coordinate, the coordinate of the data points in the new basis. So here we can read from my original first point, first data point is, the coordinate in the original data feature space is 10, 11, 10. So in my new feature space, which is the full PC space, it becomes negative 10.818, 7.917, negative 0.072. So that's it. And this is the whole matrix, the score matrix. It shows the new coordinate of every data. So that is the thing of the first example. The second one is, actually similar things. I guess here to save my time, I don't have to code it because it will take some time to test the Quaver, I believe. Yeah, these two lines about the Quaver I wrote here, they're to plot those arrows or Quavers. Let me just have a brief like introduction of this. So first of all, we're gonna generate the data, randomly generate 1,000 multivariate normal distribution data from this multi-normal distribution, and then we have X bar. Why? Because we were gonna use X bar later to reconstruct. Actually, wait a minute. Yeah, why did I compute X bar in this example? I guess we don't have actually. Yeah, actually I don't need it. I don't believe in this example we need X bar. I have no idea why did I compute X bar. Sure, here we don't need X bar. And then we model equal to PCA, meaning that we're gonna have a full PCA, a basis and a fit model, and then model components. So here are the PCs printed. Okay, so after it, we plot the data and the PCs in the original feature space, which is this one. So first of all, create a 2x2 subplot, and then we just have this. Be careful here. I wrote one thing called a Z order. So in the plot and also similar things, Quiver, you can use Z order to tell the order, of those things plot. To force the order. So here I wrote a Z order equal to 1. And then here, by Quiver, I actually plot those kind of arrows. I make the Z order to be like 11 and the 12. That means what? That means that I'm gonna plot those points first, and then I will add the Quiver to plot those arrows. Because if you do not add this Z, I don't know why actually to add this. These plots gonna cover the Quiver. Even if I, from the code, I wrote this first, so that, in my view, I don't have to have the Z order because I think if you use a plot this one, so it will here first, so it will plot this first and then plot the two quavers. The truth is not. The truth is you can test the code after, after a class. If you remove this Z order, these two quavers will be covered by these red points. That's something very interesting. So that's the only thing. And after here's a quiver, here's a full documentation if you want to check it. It's basically, from A to B and then give you a scale and, here and then have the units. So you can just adjust the scale and the units by uh, uh, adjust the scale, sorry, so that you can, adjust the size of these two quavers where they're these two. So here it shows you this is the first PC, this is the second PC, and indeed you can see. This one I make this to be bigger than this one on purpose again, it's because I just want to show, to indicate the size. This direction is more like the variance is larger than this direction. However, in the real case, the PCs must be unit, vector as we've already defined. Okay, so finally, here, here the second one here. So I want to make it clear that, so pay attention to the type the y and x title, y title here. This is the original feature one, original feature two. Okay, in the second subplot, you can see this is the first PC. See it? In other words, I've already rotate, the coordinate from the original one to these two directions already. And hence you can clearly see, this is the training data, and the first PC has clearly bigger variance, much bigger variance than the second PC. Okay, and the third one is actually to show you the variance or the data projection on the first PC, which is just project onto this. And you can see, indeed, the variance is way bigger. And the third one is the last one is the second PC. The second PC here, pay attention to the scale because people may say, hey, looks, this is also big, but don't forget, don't forget this. Here, the scale is 20, while here, the scale is only 5. You see what I mean? In other words, if you put this picture here, it may be something like this, very, very small. But the original thing is here. So this is just to show you, again, the ideas of the PCs, which is a coordinate system rotation from original PC to a new PC, which is from the original feature space to the new feature space, which is the PC feature space. And then we can see why do we do it? Because in this case, we can clearly see the difference of the dimensions of the variances. And then we can perform the dimensionality reduction by this, that, explain the variance on a threshold. That's a thing. Okay, next, let's see. Oh, wait, before the example, I need to introduce one more thing. Let's see one thing, which is called a data reconstruction using incomplete PCs. So as we mentioned, previously, we can reduce, the data dimensionality from P dimensional data to K dimensional data, where K is less than or equal to P. And in practical, K can be less than P. For example, if your P is 1,000, for example, your K can be only 10. Some could be only 10, something like that. In other words, assuming we know these, K PCs from V1 to VK, the original feature space have uh, oh, wait, wait. Oh, wait a minute. Assuming we know this and we have the corresponding spaces for all the PCs, our goal is our goal is to recover or reconstruct the original data by projecting it back to the original p dimension space. Why do we need to do it? Because we, for example, later we're gonna see if in those kind of image we want to, project it back to the original space so we can see it. Otherwise, our eyes cannot, like we cannot run the PC in our brain, you know what I mean? Otherwise, we cannot really see it or really handle it, using the original feature space. So this process is actually very important in applications such as image and signal processing. And to calculate the scores of the K PCs, remember we have used this one, XPC, which is here in the code we use X transform actually here. Here we go, where we are X trans model.transform X. So here we have XPC equal to ZV, which is nothing but a score, which is mentioned, where XPC is in N by K. Why? Because we only, we only use the first k pieces, and hence the number of columns as only k at the score matrix, right? And be careful here, row I representing coordinates of the data on point I in the new KPC basis. And then this V is nothing but just, row vector, column vectors of the PCs. Okay, so now we want to reconstruct the data in the original P dimensional space. In other words, we need to project it from PC basis back to my original feature basis using only the first k pieces. First of all, if k equals to p, then you don't have to compute. Why? Because it must be exactly the same. From the original data back to the original data. It's nothing. Of course, in real applications, k is much less than p. Then that's another story. So how can my project it back to the original feature space? What you need to do is simple, just to reverse this process. First of all, don't forget this is with respect to z, and the z is what? Z is actually something like minus k, minus x bar, which is right here. You can see here. Z is this form, so that you need to add back in order to get to the original x. You need to add back this x bar, which is right here. You need to add back x bar. The second thing is look at here. I already make it to z x what PC equal to zv, right? And hence, in order to get to z and add back, I get to the x. We need to what? We need to write what I mean this. Let me just open the Word document. I'd better write it down to make it more clear. So here I've already have x PC equal to ZV. That's what we have. So I'm gonna ask you, hey, what is Z? So from here, I can immediately get Z equal to what? X PC V inverse, right? So what you do is both sides of the equation, right, multiply the inverse matrix of V. Okay, so one interesting thing here, first of all, V inverse must exist. Why? Because V is a what? V is a coordinate, is a basis of the what? Of the either better. Let me think about this. Give me 1 second. Give me 1 second. Let's say let me make it in this way. Let's say let me call the PC full. This is also V full. Yes. Otherwise, I cannot make it inverse. It will be something. Okay. So I need to have Z equal to PC full and this. And then just to let you know, since here V full means K equal to P, PC full everything means assuming K equal to P, here's the case. And then I can write in this way, X PC full times VT. V full, sorry, I should put all the full. V full T. Again, full means K equal to P, okay, which means we don't have dimension, nullity, dimension reduction. Everything is just a full space, okay. So Y inverse equal to T. The reason because V is a projection matrix. It forms a projection space, but a projection basis. It has a projection space, meaning that first of all, each column of V must be unit a column, a unit vector, and also any two columns, they must be orthogonal. Just consider, let's say, the eigenvector. So sorry, consider the identity matrix I equal to what? I equal to just a 1, 1, 1, 1. What I mean is let me see how to make it in the matrix. Where am it? Where can I consider the identity matrix? What I mean this 1, 1, 1. All other elements are 0. So this one, of course, the inverse is it's transpose. Just to expand it, for any orthonormal matrix, for all any those kind of basis unit basis matrix composed by unit vectors, you always have this conclusion, which is inverse equals to transpose. And hence, now consider this case, the case in which K is less, here is the case for the case K equal to P, okay? Let me add something here. Okay, now for the case which is K less than P, we're gonna have what? We're gonna have this. I can simply just remove a lot of things here. So I have XPC equal to ZV. Be careful here, we can no longer make it to be inverse. Why? Because you can see the dimension of V. It's not a square matrix anymore. So, I mean, inverse only exists in square matrix. This is not a square matrix. So, of course, I don't have this. However, the thing is VTV can still make it back. So what I mean is here, I can still make this instead of V minus, I can have this. V, 1 minute, 1 minute, 1 minute, wait 1 minute. Yes, VT here. And I can still have this VT equals to 1 minute, X bar V. Okay, give me 1 second, give me 1 second. XPC V here. So I can still have this. I can still write in this way. So this is something that I want to cancel this V. And then you can get what? And then you can get X equal to Z plus X bar, and hence it equal to X PC VT plus X bar. So that's how we get this formula. Actually, we use the property that V is what? V is a projection matrix. That's how we get it. Again, this math, if you're not familiar, not a big deal. As long as you know the idea. The basic idea is that I'm gonna first of all, I project it from the original space. Let me just show an example. Do I have an example here? So first of all, I projected onto, this is the original, space, original feature two, original feature one, and then projected first onto my new base space. So I have V1, V2, right? Now I realize, hey, V2 is very small. Let's say by the threshold or something, somehow I can, remove it. I only need a V1. So in your new base, you only have V1, which is a dimensionality reduction from 2D to 1D, right? Okay, so now you already got a 1D. You want to project it back to this feature space. How will you do it? That's the point. And this formula, where it is, this formula shows how you can get your reconstructed matrix back, which is just a z times v times vt plus x bar. That's it. X bar super easy to get. V we can already get as long as you give me the k, which is how many PCs are needed. I directly have the v, and I can have v times vt, and then here get the z as well, which is from the original data. Then by this way, we can directly get x reconstruct. That's the thing. Here I should wrote it. The matrix VT acts like a projection matrix. Especially if we apply all the PCs here, then this equal to I. I is the identity matrix with the P dimensions. And hence the data will be completely recovered. However, if K is less than P, the constructed data is generally different from the original data, meaning the recovery is not exact. But no worry, in many, many cases, even if it's not exact, you will see today the examples, the results is actually pretty good. And a very, very good example you will actually get from your final exam, the last question, which is I remember a picture of Mona Lisa's smile, and you can see Mona Lisa's smile. In the Mona Lisa smile, you can use this one to make it very beautifully. Let me see whether this is, yes. So you will use PCA to analyze this picture, the most famous picture, and then you can see actually you only need a very small amount of the PCs, and you can recover this picture very, very good. If you if you do it correctly, okay, here's like a hint. If you see a result very good, that means your answer to problem number three is correct. If your result is very bad, then probably something's wrong. But anyway, so let's see some applications of PCA. The first application is the data visualization. As we mentioned, to direct show display a plot or a figure, it must be only 2D or 3D, right? Because we cannot plot more than direct plot more than 3Ds. However, in many cases, the variance explained by just two or three PCs may be sufficient already. And hence, we can just use this way to plot the data to reduce the dimension from the high dimensional space to 2D or 3D only. But just to let you know here, is not every cases you can plot it. In many cases, it's not sufficient. Then you cannot just directly plot it. Another thing is in classification and clustering, something similar by representing data in a low dimensional PC space. Again, here k is less than or equal to p. Classification or clustering algorithms can become more efficient. So that is the thing. So for target data, we first compute its coordinate in the PC basis first, and then we can perform classification or clustering, on these reduced dimension coordinates, which is much easier. For k-means clustering several things, we can plot data in 2D or 3D space, and then help visualize clusters directly. So you even don't run something. This is the thing. However, be careful. Strictly speaking, PCA is an unsupervised learning method. So using the PC basis can simplify classification tasks significantly. However, just make it very clear that it's important to note, though, that the transformation may sometimes introduce misclassifications. So for example, in some cases, I mean, you do classification, for example, directly uh, based on the original data. Maybe your training accuracy, for example, is 98%. While you convert it to PCA first, you make it, you project it from higher dimensional space to a much lower dimensional PC space. Then you do classification again. Your training accuracy could be reduced, even significantly reduced. For example, from 98% to, for example, only 78%. It's possible. Just to let you know, be careful about this. Okay, so here we can actually show an example of the PC applied in the hand return digit recognition example. Remember this one again? So let me just code it to make sure everything's good. Good. Let me close this one first. Close. Okay. So here we're gonna import NumPy, SMP, import matplotlib, plt, and then let me make this. Well, and then I'm gonna have from sklearn.decomposition import PCA. Okay, so first of all, I need to generate the digits. So digits. So first, I need to have. Sorry, wait. I need to have what? Here I need to have. Let me see. Oh, wait. I need to import more things from sklearn.digit. Wait. What's called dataset? Yes, dataset. Import load digits. Digits, not diabetes. Okay, so I'm gonna have digit equal to load digits. Come on. Okay, I believe only three. Yes, in class three. That means I only need, to make my life easier. Why? Because I want, show different color. I don't want to show 10 colors, which is very troublesome. So I just show three colors. And hence I make n class equal to three. N class equal to three. Okay, so here I'm gonna get an x and y dot data and y equal to digits dot target. Okay, so here you can, for example, print x dot shape and y dot shape to have a look at it. So since we limit the digits to be 0, 1, 2 only, so we don't remember before we have 1797 digits. This means the what dimension. So each digit includes 64 pixels. It's 8 by 8, and hence I have here if I only include 0, 1, 2, so I only have 537 training data. So similar things, y is just a vector. So this is just vectorize the 8 by 8 pixel. Remember, we need to use x dot reshape and to show the image, right? And then in training, we need to reshape it back to a vector to what to get a training PCA training. So that is the thing. Okay. So here now, actually, I don't really need it. So what I can do is that I want to plot those kind of training digits, plot the training digits again. Actually, I press I just don't know why it doesn't show. Okay, so here I realized, remember in KNN, I actually wrote a code here. I realized actually my code has an issue. The reason because it was square, and so you actually exchange x and y. It doesn't matter. Let's see here. This is more where this is more correct. So what I want to do here is I first define the number of image per row, which is the square root of this, and I use an int to make it thinner but longer. So here I have how many I forgot again? 573, right? Yeah, 573. So you can see 537, sorry, 537 square root is 23. And hence, I want to have kind of like each image per row is going to be 23 rows. And then I will have 23 times 24 probably. 24 equal to, yeah, it's already bigger than 537. Hence, the image should have 23 columns and 24 rows. That's how we get. Of course, I mean, here I didn't brutally tell Python this is 23, 24. Instead, I just use square root of this to make it. And then let's have a look how we make it. Because I remember when I prepared this lecture, I realized that what is wrong. The code I wrote in the KNN is wrong. And then it took me some time because I accidentally make it a reversed x and y. Why? Because here's something pretty confused, to be honest, because number of image per row, that means the number of columns. Say the number of column, the number of, let's say I have 23 images per row. That means my column equal to 23, not a row equal to 23. This is pretty confusing here. So number of image per row is np dot square root of x dot shape 0. That means 537. And then to make it to be an integer, and to add an integer. This integer is somewhat because a positive number is somewhat like a floor function. And then I'm gonna have number of image per column equal to x dot shape. Come on. Okay, comes x dot shape 0 divided by number of what image per row. I need to have this. Well, I need to have a CO function to make it a four set to be 24. Otherwise, that will be float and p dot nail CO. Sorry. And also, just to let you know one thing, something here is wrong. I remember clearly as type. I must have as type integer here. Yes. The interesting thing is if you don't make it to the as type integer, it will be. Let me show you. Suppose I don't have it. Okay. Now I'm gonna print number of per row and then number of image per column. Here we go. Where's X? Okay, here we go. Okay, see it? This is correct because I use int. So it forces it to be 23. However, if I put it like this way, it gives you 24.0. It's a float. And then because we're gonna use it to the index of the matrix and tensor operations. And the index cannot be, let's say, x from what I mean this. For example, I can have x 24. You cannot have x 24.0. You see what I mean? And hence here I have to force it. Use as type, force it to be int integer. So that now, let's say if you still print number of what per column, it will show 24 instead of 24.0. Okay. So after this, now we can make it. So for row in range of, be careful, here's number of what per column, not per row, because I clearly remember when I prepared, the image shows wrong. The image shows like what, a mirror from this direction. In other words, you can, it's like a transpose. You can understand it as like the first row here, it became the first column, and the last column in my original image was like this way, like on a part. I was thinking, how come? And I check my codes and I realized, oh, this is the thing really kind of like really confusing. At least for me, it's pretty confusing. So here, again, be careful for these things. You have the y start, meaning the coordinate of y instead of x. Why? Because it's corresponding to row. In my previous code, I wrote x start. It didn't cause a big issue because it happened to be a square matrix, so it's symmetric. You see what I mean? It doesn't matter. Here, it's not symmetric. That immediately shows the issue. Okay, so after y start, again, I wrote as what were used in the KNN. Although each image is 8 by 8, I would like to use 12 by 12 to show it to give it some margins. Otherwise, it will be very crowded. So now I have y start, and then I will have for a row in sorry, for column in range of number per row. Okay, so first of all, I need what? I need to define the index. So this means this. Okay, this means, so for example, you have, how, which row and which column. So for example, let's say I ask you this number. So I ask you, hey, how can I get this number? So we already know total how many rows, how many columns per row? 23, right? So from 0 to 22. 23, 24. I want to find the index 24. Why? Because I can directly read it from x24. Remember what is my x here? My x is just the data. You remember what we print? Remember I wrote it here. We print the dimension, which is 53764. So I want to know the index of this number in x. This, as we mentioned, it is the 25th. However, since the index starts from 0, so here's 22, 23, 24. The actual index in of this number in the X matrix is 24. That's what we need to do. In order to do this, I need to compute, right? Given the row number and the column number in this figure, I ask how to compute the X index. It's actually very simple. Why? Because you already know each row, is composed of what, 23 numbers, and then the row number start from 0. So this X index directly equal to what? The row times the number of image per row plus the column number. Done. That's it. Again, be careful. Row, column in Python both start from 0 instead of 1. Not like many other languages, 1. The first index is 0. Okay, and hence I can immediately get the X index equal to row times number of a column or row. Per row, yes, that means the column number plus column. So this is, the index of each digit in the matrix X. And now after getting this, I can just directly read it. And one thing, be careful, since it's not a square matrix, and you can see we have something empty here, right? So I do need to write something, which is if the X index is less than or equal to the maximum index. The maximum index here, we already know it's 573. What I mean this, so we already know it's 23 by 24, right? The problem is 23 by 24 is 552. For example, here, the index is already 537. 536, because it's from 0 to 536, totally 537. You cannot ask it, hey, what is the next number, which is x 537, because x, the maximum index is x 533, for 536. It doesn't have x 537. It will show error. And hence, I need to have an if, statement here, which is if the index is less than or equal to the maximum index. How to say the maximum index? You can definitely use, index something. What I do is here, I use x shape 0 minus 1. That's the maximum index. Why max shape minus 1? Because the shape is 537, right? But the maximum index is 536. Why? Again, because it starts from 0. If this is satisfied, then you do, which is to compute, to get, the X image, put it to your image tensor. Otherwise, don't do it. Okay, so now I need to have the X start. X start is actually pretty simple, which is the column start. Be careful, X is corresponding to column and Y is corresponding to row, okay? Plus 1 as well, just as what you did here, the same thing. Okay, so now I'm gonna have what I'm gonna have an image matrix. Oh, well, I haven't defined the image matrix here. I need to define an image matrix. Image matrix equal to MP dot zeros. And then let's see, I'm gonna have 12 because I do want everything to be 12 instead of 8 to give it some margin. Dot number, wait a minute, it should be colon or row. Wait, something wrong. I need to put it here. Let me see, number of image per, it should be per column. Yeah, per column means rows. And then 12 times number of image per row here. Of course, you don't have to write X, 12. You can write, for example, size. You know what I mean? You can make it to be a variable. Let's say size equal to this and everything size times this. I mean, here, I'm just a bit lazy. You know, you can even write it to be a function or class or whatever. I'm just a bit lazy here. So I'm going to have image here, y start to y start plus 8. Or other places, space is going to be what? Going to be 0. Remember, because I created to be 0. I'll need to change this from here, here to x start. Again, y are the rows, x are the columns, plus 8. These going to be changed equal to x of the x index. Eh, right? So x index is something already computed, which is this. And then dot reshape, y, come on. Okay. Y reshape because I need to show it. To show it, you need to make it to be 8 by 8 instead of 1 by 64. So that's the thing. Okay, now I can just plot it. PLT dot figure, I create a figure first, and then PLT dot in show. You can use a CMap equal to map equal to binary. Then give it a title like PLT dot title. Let's say the training digits from O. Okay. And then let's make it a PLT dot show. Okay, so where it is? Whoa. What PL PLT dot how come this one is wrong? Wait a minute, wait a minute. Why? Has no it math okay, that's the thing. Pretty dumb. Okay, here we go. So now you can see this is exactly what we're looking for, right? So we're gonna write according to rows and the final number here is 537, and since 23 by 24 is 555, and hence we need to have something blank. You know, by comparison, if you don't have this, okay, if you suppose I don't have this, let me make it indent. It will show error, which is beyond the bound. See it? It's out of bounds for access with size 537. Why? It's because I don't have it. It's because the coordinate comes here. Here should be empty. You should do nothing, but you still force it to read it from x. But x the maximum is x of 536. It doesn't have x of 537, and hence it shows you out of bounds. So that's the thing. Okay, let me just okay. Okay, so this is the first thing that we finished. And second thing is what we want to do here is we want to exactly show, because here again, I mean, by our eyes, we can know, for example, this is 0, 1, 2, 3, whatever. But what if instead of, the 64 dimensional original feature space, what if I just want to projected onto 2D or 3D. So you may ask me, so why you project 2D, 3D? Why not 5D, 10D? So really because if I project to be 2D, 3D, then very interesting. We can visualize it. We can see how everything looks like, right? So if I want to play this game, can I do it? Of course you can do it. So that's what we want to do, which is to train the data by let's say by PCA under 2 and 3 PCs. Okay, so now I'm gonna train, let's say, a model. First of all, let's do the 2 PCs model equal to PCA and components. Okay, and and components. Why doesn't it show me? It should show me. Did I put anything wrong with it? PCA, yes. That's interesting because technically it should immediately show me. Yeah, here we go. And components. So why doesn't it show me anything? Okay, let me just manual. Okay, it's a bit too slow. Maybe server something equal to 2, and then I can just model dot fit x, and then I can just first of all I want to plot the PCs, right? So I have xPC equal to model dot trans form. Be careful here. I put I put I one minute. Actually, I should, one minute. I'd better not to mention, I'd better call it X transform instead of XPC because if I wrote XPC, I remember in my notation, I make XPC to what? To be the PCs instead of, let me see what notation I use. Oh, I also use X transform here. PCs. Okay, if that case, let me keep the same notation because I remember I wrote XPC as in my what notation here. In my notation here is XPCs. Yeah, okay. Let me continue the notation then. XPC equal to a model.transform, and then I can just create a figure. And then what I want to do is that I want to plot those points and then use different colors to indicate it. Be very careful. You cannot just make color based on this. Why you cannot? Because actually, one minute. Yeah, actually, correct. I should have plot based on this because this is I haven't done anything like clustering something. Okay. Sure. I can cheat here. The reason because it's really not cheating. The reason because my purpose is to make project it from 64 dimensional space to a 2D or 3D space PC space. And hence, true, in order to show different, digits clearly, I have to use the Y label here. Otherwise, it will be very wrong. Okay, so first of all, I can just plot, create an axis, x equal to figure dot add subplot. I used how many? Let me see here. Okay, 2 by 2, so that I can have 1 to 1, and then I will 1 to 1, and then I will make this, which is x dot plot. For class 1, I have xpc. So here's the trick. You can use y equal to 0. So this tells you uh, which is where this is the target. So this tells you which axis you should choose. So y equal to 0, that means it belongs to digit number 0, class 1. Or you can just simply call it digit 0, which is easier. So this tells you for the PCs, which PCs y equal to 0, these PCs. And then here's, of course, x, and then x, p. Come on. No, not in x, PC. Y equal to 0, 1. And then now we can make it to be r dot and then label equal to, let's say, digit 0. And I'm going to copy and paste digit 1, digit 2. Oops. Okay, so this is something what we do. And then we can always have, legend. And then I can, let me see here. What do I have? Oh, access equal and then access variable. Okay. X dot access equal is just to make sure that the scales of the x and the y is not too different. Otherwise, it will show you something very a very thin picture, which I don't like. So this make the axis equal, and then set up the label, and then let's say PC1 and then PC2. And then final title, training digits 0, 1, 2 in the first two PC bases. Okay, so we can just show it. Here we go. And you can see that this part is empty because I subplot 1 by 2. So as you can see, digit 0 is here, digit 1 is here, digit 2 is here. You see what I mean? Actually, even in two PC bases, I can already, I mean, even if this is something like clustering, I can already determine something. Why? Because if you plot, the classification region, you're gonna see, you know, zeros are always, the right side of here, while your digit one is something around here, digit two is something around here. So I can probably plot something like this way. I just randomly, write it. Okay, so I can probably make a decision within something like this. You see what I mean? And this is very good result is because here, I mean, if I ask you, hey, what is that? I don't give you any background. I believe nobody gonna tell me, hey, you know what? This is digital zero. This is digital one. This is digital two. Nobody can understand it. However, the point is that I have successfully reduced the dimensionality from 64D to 2D only. You see how good it is. And instead, so in future work, instead of reading those numbers, I can just read this. This is kind of like a secret secret language. Nobody can understand that. That's how. So from computers view, this and this they're equivalent. I mean, just lower dimensional reduction. But from humans' eyes, everybody can recognize those digits, but nobody can recognize. I tell you, hey, this is zero, this is one, this is two. Who understands it? You see what I mean? So this is something we can show how different they are under PC basis. And the magical thing is under the three PC digits. Let me just copy and paste here. They're basically the same. I'm just gonna say under two PCs. So let me say, okay, here is under three PCs. Three piece here number components equal to two, and then I can make this, and then let me see here. What I can do here is let me see here. Mono equals three, and I see here transform. Still the same thing, 1 to 2 instead of 1 to no, I don't need this one anymore. 1 to 2. Okay, so here instead of this, I need to have one more dimension, which is x PC y equal to 0, 2. And then I'm gonna just copy and paste. Okay, digits 1, 2, 3, x dot legend still the same, and then equal PC1, PC2, and then need one more x dot set z label PC3 in the first of three PC bases. Okay, plotted. Uh-oh, great. No, Z label? Did I spell something wrong? It must be the same thing. It must be something wrong. Actually, why? Projection period. Sorry, I forgot. So I need to tell Python this is a 3D. Otherwise, the water will be wrong. And I still consider it as 2D. Okay, here we go. Let's see a magic thing here. So this is 3D, right? We can just rotate it. You can see they're actually already pretty different. You see what I mean? Especially from this angle. You see? Zeros are all here. Which one is one? The green is one. Ones are here and the twos are here. You can see they're actually already very different from 3D. And hence I actually haven't. That's a good question. I haven't actually do classification. I haven't performed classification on the low dimensional space. Yeah, if I teach this class next year again, I will do extend this example by, let's say I'm going to train those kind of digits 0, 1, 2 on the new PC, let's say three PCs or five PCs, and I'm going to see how the training accuracy are improved. I bet you even if under the three PCs the training accuracy is going to be pretty good because you can clearly see here we have 537 points, right? The only intersection points are these points, and you can see those points, the numbers probably less than 10. I cannot count, but corresponding here is this area. You can see where green and the blue points are pretty. Actually, if you see in two PC, you can see there are a lot of points, intersection here. If you do the classification to train it, it will probably show you misclassification, and hence the training accuracy in the two PC basis will be lower. However, in three, I bet you it's a very high already because you really, I mean, those points you give it one more direction, the dimension, you can see that they're pretty separate, not like 2D altogether. You see what I mean? They're actually all pretty separate. So yeah, I bet you probably we don't need a 64D. We probably need only 5D or 10, I mean, PC dimensions. the training accuracy can be already very good. So what people may ask, so what is the meaning? The meaning is that instead of the 64 digits, which is the whole picture, you just need to convert it to be much lower dimensions, and you can train things very well. And then you're gonna ask me, so what? What's gonna happen is that, well, this is something about the X reconstruction using this formula here. Uh, if you give me a new target data, let's say suppose you give me a data something like that. This is 8, right? This is 1. You give me a data of this. I can convert it based on the PCs already. I can convert to be 3 PCs using this formula. And then based on the new data, I can do the classification on the 3 PCs. You see what I mean? The truth is that the time it will produce a very long time, a big time reduction because your space is much smaller. Here's, I mean, from 64 to 3, maybe not big deal. In the real cases, it can be from millions of, original space to maybe 100 space. It can save you from years of computing time to several hours. So this could be a huge reduction of the computing time. While as long as you know your training accuracy is not sacrificed too much, then it's fine. So that's the thing. Okay, so after it, let me show one more thing. Okay, so first of all, I showed. Wait, did I code? I haven't coded yet. I forgot. So here, so we finished this part, right? Okay, so here we go. It is the, I want to, let me just call it to make my life easier. So after this, what I want to do is that I want to, let's say, explicitly show the image, mean, which is X bar, and the 3 PC in the original feature space. Okay, so why I say original feature space, with my code, you will see why it is the original feature space. The truth is that even if I have 3D, I want to remake it to be 64D, 8 by 8 to plot it. So what I'm going to do is first of all, create a new figure, plt.figure here. I will create a brand new plot, including, the 3 PCs and the X bar. So first of all, I need to compute the X bar. Remember what is X bar? It's nothing but a summation of all the data and then divided by n, right? So it's simply NP mean of X, and then pay attention. So what I'm gonna have is this. Let me plot it. What I'm gonna have is 64, 64, 64, like this, right? So what I want to do is I want to summation everything by columns and then divide by it. So here you must have X is equal to 0. And hence, I'm going to sum it by this. And finally, I get just, the 0 or the rows of the mean here. Okay, so I'm going to have this X bar, and then I can add the what X subplot equal to, I need 4 figures, 1 for X mean and 3 for the PCs. I mean, I'm going to plot the 3 PCs instead of more. So it will be dot add subplot, and then 1 for 1. This is the X bar. I'm gonna plot it first. So I already get an X bar, so I'm gonna have image show the which is X bar. Be careful, you cannot directly make X bar because X bar the shape is wrong. Okay, the shape is still what 1 by 64. So first one you reshape it to 8 by 8. And then again, I'll make a CMap to binary so that it will be easier. Otherwise, it will be just colorful, very weird color. And then I'm gonna have X dot set title, which is, let's say, the mean image, mean digits, so let's say, mean digit image, let's say. Okay, so let me have a look at it first. Okay, I know it's ugly, but unfortunately, that is the mean of, a 0, 1, 2. Okay, so now I'm gonna plot the 3 PCs, right? For let's say J in range of 3 PCs. First of all, gotta actually just copy and paste. Figured out here as what it should be J plus 2 because my first gonna be J start from 0, but my real number should be start from 2, so J plus 2. And here I'm gonna what model dot component. Model dot components. Okay, so here the J's PC. So components J dot reshape A by 8 C map of this, and then here I make the what here as let's say PCJ. That's it. And then I can just plot it. Okay. Oops, here we go. Oh, that's F. Okay, here we go. So now we have this, the original image, PC0, PC1, PC2. So in other words, for any data, any digits, for any, the training data, I can make it to be this plus a mu, the coordinate plus p. Okay, well, I mean this. I remember, I believe, yeah, here we go. So for any data x, which is, 1 by 64, I can revel it to be a vector, right? I can make it to be x bar plus mu1 v1 plus mu2 v2 plus mu3 v3. So what does it exactly mean? Okay, so here, X bar is just, is just this one, the mean digits that we have. V1 is actually the image of PC. Here what I use PC0, and then I should have J plus one because I want to make it to be PC123 instead of PC012. Okay, so this is your mu1, V1, V2, V3. Again, V1, 2, 3 are 1 by 64 as well. And this mu is what the coordinate of my x new target data, the target data project onto my mu, onto my v, which is my PC vectors v1, v2, v3. So mu j equal to nothing, just inner product of your target data x and vj. The vj means the j's PC. So actually that's the meaning. Any data can be composed by or can be reconstructed by this plus mu, the coordinate of this plus coordinate this and coordinate this. That's the meaning of PCA. Here it's equivalent to this, this formula here. That's exactly the same. You see what I mean? Because here my V means only V1, V2, V3 because I only consider three PCs. X bar is just X bar, and then XPC is just these things. So that's the thing. And I know people may still say, "Hey, I'm not comfortable still. I want to see a detailed reconstruction." No problem. Let's see the next example in which we handle the database, the data called people, and so these are the building data set in scikit-learn library. I'm not sure. Do you still know them? These are politicians. I mean, world famous politicians about 20 years ago. So we're gonna use PCA to. I forgot how many PCs did I use? 16D. So the original data set includes 1850, data. And then I will reduce from 1850 to 16B, which is this 16 PCs. And then I will use this formula, which is right here, and which is actually nothing but this one. They're exactly the same. I will use this formula to reconstruct all the faces. And here's the result. Reconstructed faces, which is here. Honestly, the result is not that good because we use two little pieces. I believe anyway. Let's code it. Let me just have a review of this. I just want to make sure of okay. In case I forget the code, I can always just cheat it. So let's see here. So first of all, just copy and paste. Okay, instead of load the digits here, I must have uh or I forgot fetch or load the people or something. Fetch LFW people. Fetch LFW people is here. Okay, so similar things. I'm gonna load training bases. So I have people equal to this fetch what have people. And then let me see here. Median face per person 70, resize 0.4. Okay. Mean face per person is 70, resize 0.4. To make it smaller, otherwise it's going to be pretty big. So again, I have x equal to people dot data and y equal to people.target. You may ask me, so why do you need a y? Later we'll see why. Because use the y, it shows the label of every person. Then I will coordinate y with this something I'm going to put here, which is names equal to I will put this, I will play together y and the names and then fetch the correct data from. I mean, you will see it later. Target, what's called target names or target name. Let me see. Target names. Okay. Target names. So this is to store the names. So I can simply print this. Let's say print y and then print names, and you will see it. Okay, so y is nothing but these things, but names as actually the name set. Here we can see 1, 2, 3, 4, 5, 6, 7, 7 people. And then this is nothing but the target of this. Here we can actually make print y dot min and y dot max. And you can see the min 0, max is 6. So this one, person 0, person 1, person 2, till person 6. Okay, so now we have all these. Let me see here. I need to. Okay, anyway, to save our time, let me just put it in the other screen. Sorry about it. Okay, so now I have these names, and I can have n, height, and weight. This is to indicate the number of images, the height of each image, and the width of each image. Dot people dot images dot shape. And then of course you can just print and height with width, and I will show you. Okay, so we totally have 88 faces, and the height of the image is 50. The width of image is 37 because I just use a resize to make it smaller. Otherwise, we cannot plot it. Otherwise, it will be very big. Okay, so here I have a print function. Print. There are totally n faces in the training data set. Each with dimensions, height times width equal to height times width. Okay, here we go. So there are totally I can remove this. There are totally 1288 faces in the training data set, each with dimension 50 times 37 equal to 1850D. So this is the thing. Okay, so now after this, I want to explicitly show the faces, right? So I'm gonna have, let's say, plot. Let's say use subplot the first. Here, let me see how many 50 training faces. So this is actually super simple. Create a figure, and then subplot, make a for loop for I in range of 50, and then X add a subgroup, subplot on a subgroup, 5, 10, I plus 1. Okay, so now I have dot image show. I have xi dot reshape, don't forget it. Here, instead of 8 by 8, I can have height and weight, height. No, weight, height and width, come on, okay. And a similar thing, CMap equal to binary. Wait 1 minute, sorry. Lucky I'm having my chilling mode. I use a CM here so that I do need to add a CM from Matplotlib. CM is kind of like a color map here. Here I use a gray color map, CM the gray color map. And then here I just make it a name. Okay, here we go. Be very, very careful. You have the names, right? But it's absolutely not names I. Why not names I? Because here my name, remember, names only include I names. Instead of name I, it should be name YI. Now you get a point of why do I want to include this Y? Because this Y shows you the label. So for example, remember Y start from 0 to 6. the you know a vector. It shows for each data what is the name label. And then suppose y equal to 1, then it's going to be, I forgot who's the name. Then what I'm going to do is that according to yi, I will put the yi, the label into names, which is from 0 to 6, and then show me the correct name. So that's why I need to have it. And I'm cheating here, and I see that I also have axis off because I don't want to have those kind of XY axis very troublesome. I just need to see the face, and that's it. And then I have a figure dot subtitle. Subtitle means the title for all the whole subplot. Why? Because later this is the original figure. Later we will show the reconstructed figure by, let's say, 16 pieces. If you don't show it, I mean, it's easy to get confused. If let's say 100 pieces, maybe the result is good. You see what I mean? So I want to make it clear. So let me put it original faces. Okay, so that I also have tight layout, and then I can just make a plt.show. Okay, so here you can have all those faces, and this is the original faces. So the result is pretty good. Okay, so now next, what I want to do is I want to train the PCs instead of the original things. So what I'm going to do is here train the PCA model and subplot. Let me see whether I can make it to be subplot the first 16 PCs. Don't worry, we can play something for fun, which is use more than 16 PCs to play it. Model equal to PCA, so n components equal to 16, and then we have model of fit x, and then create a new figure. I can guess I can just let me see what I can copy and paste. Yeah, I probably can. So I in range instead of 50, I'm gonna have 64. This is 16. Here I have 4 by 4. I plus 1, and let me see here. Instead of this, I want to create the PC. So it will be model the components. Here I the reshape height white correct right. Here names wrong. It's not names. It's not the specific name. Instead, it's the PC. Where since I comes from 0, so it's called plus 1 and the type layout. And then I don't need any super titles, or you can just say PCs. PCs. There we go. Okay, so okay, here we go. And by the way, this is the super title me and the similar things. Orange original faces. So again, it's the title for all the whole subplot, not each subplot. So that's the thing. Okay, and and this is the what? This is the first 16 PCs, the result. And let me see here. Uh I have these things. Okay, so now you're gonna ask me, so okay, you have 16 pieces. So what? I mean, is there a way you can just reconstruct, right, the faces? And here we go. The next step, what I'm gonna do is I want to reconstruct those faces, the 50 faces that we have here. So here I'm gonna reconstruct the faces by the first 16 PCs and subplot the first 50 faces. Okay, so first of all, we need to have a look at the formula. Let me put it back on my slide. So the formula is this: reconstruct equal to x bar plus xpc times v. So here, actually, in Python MP, we can use at notation to indicate matrix multiplication. But X bar, we still have to handle it. Let me turn on my cheating mode to save my time again. So here, what I can do is first of all to get a X bar MP dot mean, and then X is equal to 0. Why? Because it's directed by the columns. And then I want to keep all the column things, so it's going to be 0. And then I can have what? Actually, if you want, I can just print X bar dot shape. Anyway, let me just turn off something. One minute. So you can see it's 1850. You see it? So this is the X bar things. Okay, so now what I want to do is what I want to do is I want to create the XPC because I need three things to get the reconstructed matrix, which are X bar, XPC, and V. XPC, how can we get it? Is by the transform, right? Did we have it, which is the XPC equal to add the transform of X model dot transform, and then finally V is what? It's nothing but just a component matrix, model component matrix. And then let's see how can make it step by step here. So I have where's Michael? Oh, it's here. So I have the X bar. I need to have the XPC model dot transform X. So I have XPC. Finally, I need the V. However, you know what? V is something you can directly get it from model dot components. And hence I have X reconstructed equal to X. I just use this formula, X bar plus XPC times V. So I just directly have it. X bar plus XPC. Be careful here, times is not these times. It's a matrix multiplication. Since all of them are numpy, I can have this at model.components. Okay, so in scikit-learn library, all of these are what model components, they are composed by the rows. In other words, so you see, by definition, our vectors should be all column vectors, right? This V. And I use VT to indicate it becomes a row vector. However, the good thing is model.components itself is, I mean, it's a definition scikit-learn library. It's already row vector so that you don't have to transpose it to use dot t anymore. You see what I mean? Otherwise, remember, we need to have something dot t, remember, to make it to be a transpose, right? But here I don't need. Why? Because this itself is already transposed. Okay, so now I have this. Then let me see, how can I make it? So I already have this. So now I can already get a reconstructed the matrix here, and then I can simply just plot it. Use the what the reshape image show and the reshape. Yes, I should be able to. Yes. So I'll create a figure fig.plt dot figure, and then I can write a for again for I in a range of 15. Actually, I can just copy and paste. Okay, add here is 510. Here, instead of this, I'm gonna have x reconstruct. X reconstruct. Okay, I to the shape of height, width, and cm dot gray. Yes, and here I'm gonna have the names. Yi again. Names. Yi. Okay, and that's this off, and I have another like the figure tight layout. Super title reconstructed basis. Okay, so you will see the reconstructed phases, which is oh shit, what is this? Okay, so that means this is reconstructed phases. Okay, so now if I compare this, if I want to compare this reconstructed phases with the original phases, uh, well, Chavez, the reconstruction is not good. Blair, not too bad. Bush is actually ratchet good. You can see I can recognize Bush. Powell, I cannot recognize this Powell. Sharon, okay, I cannot. This looks more like a George W. Bush actually. So, excuse me. We can see that the number of pieces, so if I just use 16 pieces, the result is not that good. You see what I mean? Okay, so no problem. We can create it to be more than 16. What I can make it to be more figures. So to this point, let me just write a comment here so that I'm not gonna have this plot. I want to just save those plots. Okay, so now I can give me 1 second. Let me see how can I train my models here, which are fixed 60. Yes. Okay, instead of 16, I make it to be 100. 100 PCs. I'm not gonna plot all those PCs, and then I'm gonna have 100 here, and then 50 something. Give me 1 second. Give me 1 second. PC model components. Yes. So the only thing I do change is this n components equal to 100 because here I still have plot these faces. Okay, let's see. But it may take much more time, much longer time. Okay, here we go. Not much longer. I show it because I don't do plot. Okay, here we go. Guys, have a look here. Uh, the result is way, way, way better. See it? I can clearly see this is Chavez, this is Blair, George W. Bush, Colin Powell. Already see it? It's already very good. The point is the original space is 1850. It's a 1850 dimensional data. This is the original. I mean, here I only use 100 dimensional, which is a shrinkage of 1 over 18. I mean, it's you only use, I don't know how many, actually 100. You only use 5%. You reduce already the dimensionality by 95% already. And look at your result. Your result is so good. You see what I mean? This is actually a huge thing. And in your final exam by Mona Lisa Smile, you can see it's also a very big dimensional reduction, and the result is amazing. You will see it. Again, just give you a hint. If your result is very good, that means you did it correctly. So yeah, this is the same. And then finally, I believe I showed one more thing, which is let me see here the 16 space. Okay. So here I chose one face. Here to save my time, I'm not coded, but I mean it's very simple. Just copy and paste. So my point is this. So I showed a specific case to explicitly show the reconstruction with the first 16 pieces. You may ask me, so why you chose 16? Because of this example, I do want to show exactly the explicit, decomposition of this. So we chose, let me see, what did I choose? Phase number two decompose as two. In other words, I chose this phase, one, two, three, this phase. I chose this phase, specific phase for decomposition. So this is really, really. Okay. So my original phase is this. And remember, my decomposition phase is this phase, right? Okay. My reconstructed phase is this phase. This is the either index 0, 1, 2. George W. Bush. Yeah, because here I have phase number to be decomposed as 2. And here what I have X reconstruction phase number. This is the index. So I did have selected this phase to decompose to decompose. Okay. So the left hand side is this phase X reconstructed, right hand side is this. So these are the first 16 PCs, which is right here. So here I show the score. More clearly, I should write it to be efficient, which is right here. Let me see my code here. Give me 1 second. Okay, so here XPC something, comma I, because total I have 16 PCs. So here is the I PCs. I range from 0 to 16, to range 16. So I show 2 points. So this is actually the score of, which is actually nothing but a coordinate. So in other words, this picture, the coordinate, remember this formula? Mu1, mu2 till mu16, right? So this number, the score is the mu1, mu2, mu3 till mu16. This is the coefficient or the score of this picture projected onto this PC base. And you can see this is a clear reconstruction. So how did I get this picture? What I do is negative 2.37 times this picture plus negative 0.81 times this picture plus until this plus 0.37 times this picture plus x bar. Remember we got x bar before? Where's my x bar? Actually, I showed X bar here. I didn't show it. Anyway, but just to let you know, I mean, did I show X bar? I did. How come I didn't show X bar? I should have showed X bar somewhere. Oh, also forgot the printed output here. Actually, I have this. There are how many faces of somewhere. So for example, there are totally those number of faces. 77 faces belong to Ariel Sharon, and the 236 faces belong to Colin Powell. I mean, where's the code? The code is here. I forgot this form. Loop. Not a big deal. I mean, it's very easy to perform it. And I didn't plot it, but anyway, just to you know, let me see here. So yeah, oh, here we go. Here we go. Okay, plt.xshowxbar.reshape so that this shows your x bar. So in other words, remember, this is how I exactly compose this x, which is x bar plus mu1 v1, and each v1 is actually a PC face, and the mu is the score. X bar is just this interesting face, and then this is I explicitly show the reconstruction. That's it. Of course, remember here we already did the 100 PC. You can also do it. The reason I didn't show this is because I mean, on one slide it's too small. If I cannot just print a score and I show 100 such faces. That's why I showed 16. I mean, because I have enough space to put everything on one page of the slide. That's the reason. If you want, you can definitely make it every score. You can for everything you can where it is here for every name, you can get a score of this. You see what I mean? For example, here, what you can do is just to, just with this, with score, this thing, so that you can get, I can just make it. Reconstruct faces name here. Let's say score. Let me just make it a score. And then here's nothing but X, where am it, XPC. XPC, and then I'm gonna have, wait a minute. Uh, oh no, you cannot. You cannot. Sorry. Because this is not a decomposition. This did. This is not a decomposition. What I did here was because I specifically decompose this face. In other words, if you make it to like this way, right? You can decompose for a specific face, but you cannot. It's gonna be a 3D or for 3D. No, it will be a 3D because for each face you will have another like for each of this face you will have a decomposition of the faces here, so it will be like it will be 40 tensor instead of 3D, it will be 40. So that's the thing, but just to let you know, the meaning of this is, I want to explicitly show this is for each v it is a PC face and x bar and this picture, and I decompose this one by one, score mu, everything shows. So that's everything about the PC face. PCA show the faces and then chose a K, which is the number of PC I need, and then I showed a reconstruction of this, and then specifically for this face, I implicitly show the range construction by the linear function here, which is just where this linear function. Okay, that's everything here. So finally, I remember there's something very interesting in the YouTube thing here. So this is a pretty old one, but this is a super good. So it uses something like, I believe originally it uses the neural network, but the mean is pretty close. So this is all people's different face. I make it from image. I make an image to be different, like latent spaces here because due to time limit, I wish I have 2 more weeks so I can introduce, have a brief introduction to the neural network, but nothing. It's just a summation of the linear functions. And then we have these layers, and then we train from different faces on the internet. I forgot how many faces, like more than 100,000 faces here, but you can just, this works something like a PC basis. You can see each one is kind of like represented for a different meaning. You can adjust those, features, and then you can just project it onto the space here, and then you can just make your own faces. And the link is here, and I believe I showed the link. Here we go. So so we can play it by yourself instead of just watching the YouTube. I mean myself, I want to play. Okay, so let me randomly generate a face here, and I believe like it has different meaning. So this is the most important factor, and then here this can train different like even gender, the space, and then we can make different things, and then you can just adjust those things to make make a face that you have. The reason I include this in the PCA is that here I don't know how many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 16 totally. 16 times 2 is 32. It's kind of like the concept of using 62, different PCs to train different things. And I can reset at a random. Okay, so here's like a girl. I can adjust this one, make it like a boy, but you can see face part still looks similar. You can see it. Here's go. Oh, looks like the more left is a boy, the more right is a girl. So let me move like this way, and then here's something, and this looks like the clothes and neck something, and then here's something like, oh, I don't know what is that, kind of like left to right, and then here's the kind of like the head shape something. But anyway, feel free to play it by yourself, and this can show some ideas. Okay, so the formal class is complete here. Thank you so much for your time. As a reminder, I will write you a formal email after the class. The final exam has already been submitted here, uploaded here. So you can see the final exam. I want to make it very clear that no late submission is allowed for a final exam. So you need to submit it by this time. If you miss this time, then sorry, I cannot take it because we cannot delay, person one, delay 1 day, person two, delay 2 days. We cannot make that like this way, okay? So the due date, I believe, is Monday. Originally, I set it to be Sunday, but just in case, so I'll give you one more day. Start it ASAP. I don't want to hear any excuse like, oh, my network has problem, my computer has problem, something. You can do it ASAP. If you want, you can even do it today. I believe only three problems. I believe maybe problem two a little more difficult, which is ask you to manually code the two means clustering algorithm. Problem one and three is just something you can find very similar from our slides, especially this one. This one is something about Mona Lisa's smile, as I just mentioned. So what we do is what we do here is that I decompose this image by each row as a training data. So I have how many training data? I forgot to see. I have 726 rows, and hence I actually have 726 training data, and the dimension is considered as a column number, which is 982. And then I can just here what I do is just exactly the same thing as I just showed. I want to show the original grayscale image and then 5 PC reconstruction to 100 PC reconstruction, and you will see the quality of the picture is indeed step by step improved. And then you will find some, I forgot the decision, but basically, I mean, maybe 20 or 10 something, the result is already pretty good. Here, to make it my life easier, I use a grayscale as well. I believe I wrote it in the hint. Yeah, I use a grayscale image. And yeah, enjoy it. You will see something, a lot of fun. You can do it not only for this picture, you can put your personal picture to train it as well, and you can see something interesting. And then to make it kind of like, dimensional reduction, and you can compare the size, how big the size is. So okay, so I believe that's everything for today's class, and also honestly for semester. Thank you so much, and I believe I will after we submit on Monday, I will try my best to grade it on Tuesday, and then I will submit the score to the department. Of course, if you have any questions, just let me know. Okay. That's everything about today's class. By the way, do you have any questions now? I can answer now because we still have about 15 minutes. Any questions? No? Okay. That's everything about today's class. After finish this class, I believe you can go
Oh, I was
get
gonna.
the
I'm sorry.
class two. Class two will be way more. Where's my slide? So this class is Introduction to Machine Learning 1. We have another class called Introduction to Machine Learning 2. That class will be purely project based. It won't involve any Python because it assumes that you've already learned all those kind of things very well, and then it will start to work with something like a neural network, a very very brief introduction, and it will be very very project based on the image feature detection and then those kind of the sound image videos, those kind of things. So that's everything. Okay, thank you so much again, and have a great night. Bye bye.
Thank you.
Yeah, thank you so much. Bye
Yeah,
bye.
I was.
Yes, yes. Go ahead.
I'm sorry. Yeah, I was the one to send you an email. I didn't. I wasn't paying attention to the date on it. I didn't even see it. and then because I did it since last week, I just didn't put it together, and I'm so
Oh
sorry.
yes,
So
I've received your email.
yeah,
I will reply to your email, but I just want to be very, very clear that for the
yeah,
final exam, no
yeah.
late submission is accepted. I want to make it very, very clear. I don't want to,
Uh,
anybody find the front, oh, my internet has broken, my computer is broken. You can start earlier. You know what I mean? Just in case if
Absolutely.
something's broken. So okay,
Thank,
I will. I'll just see my email. I will reply to your email. So
thank you.
yeah, you're welcome. Any other questions? No?
No,
Okay. So thank you so much. That's all about the whole course. Have a good night.